Have you seen the shared screen?
Yes.
Good. So last time we have discussed about the dual nature of matter and radiation. We have seen what is black body. Black body is perfect radiator of electromagnetic radiation. This is a spectrum for electromagnetic radiation. And last time we have seen one exercise, but we don't answer it. In the cold country on a sunny day, a woman wants to melt some snow by spelunking some soot over the snow. Why? You asked me what is soot, yes?
Yeah.
So soot is some black body and will paint on the snow. When it is paint on the snow, that means the snow absorbs electromagnetic radiation from the sun. Therefore, that area will get hot. That is why the woman wants to melt some snow by splinking some soot over the snow. Did you get the point?
Yes.
So, okay, let's continue our discussion. So, what was the photoelectric effect?
The bouncing of electrons from metal when shown by an electromagnetic.
Yeah, and it is a proof for that electromagnetic radiations are particles, yes?
Yeah.
Good. So we have seen the electron emitted from the metal surface depends only the frequency of the ultraviolet radiation, not on the intensity. So the wave nature of matter, electromagnetic waves behaves as a stream of particles. The proof is photoelectric effect by Albert Einstein. And particles behaves as matter or wave. And the proof for this is electron diffraction by Louis de Broglie. So both particle and waves, the wave can be particle or particle will be a wave. And the wavelength of the particle is given by the momentum divided, the Planck's constant divided by mass times velocity, which is the same as h over the momentum p. We have seen this last time with examples. And this is a relationship between energy and the speed of light, energy and mass. Energy is the same as the mass defect times the speed of light squared. We have seen this again last time. We have seen Heisenberg uncertainty principle. It states that it is impossible to know both the exact position and exact velocity of the particle at the same time. And the uncertainty in position times uncertainty in momentum is always greater than or equal to the Planck's constant. Okay, we have seen this last time. For example, here, an estimate of position of a particle is at least 1 lambda. That means the uncertainty in position is greater than or equal to lambda. And by definition, what was the uncertainty in position? By definition, lambda is given by h divided by the momentum. For this case, the uncertainty in momentum delta p is h over lambda. Therefore, delta x times delta p is greater than or equal to the Planck's constant h. So let's see exercise 5. Light of wavelength is 5 micrometer is used to measure the positions of an electrons of wavelength is 19.7 picometer. Find the uncertainty in positions of the electron with Planck's constant 6.63 times 10 to the power of minus 34 joule second. So what is the uncertainty in position?
will bring the momentum. Momentum is equal to h over lambda. Then
H over lambda, lambda is given is 19.7 picometer. So the uncertainty in position will be h divided by the momentum is h over lambda. Then you will get the final answer. You will get this exercise. It is an example is on your textbook. You can check it. So let's see atoms and nuclei. So did you remember about the Rutherford models of an atom from grade 9 chemistry textbook?
yes,
So Rutherford models of an atom says that
the nucleus is in the middle and the electron spins at a far distance from the nucleus.
So he did an experiment for this, yes? What was that experiment? When the alpha particle is sent to the central parts of the atom, some of the alpha particle bend by 180 degree. Some of the alpha particles far from the nucleus passes or deflects with a certain angle. So why the alpha particles passes through the center of the atom reflect back? Because the nucleus is positively charged particle and the alpha particles are positively charged particle. Therefore, they repel each other, yes?
Yes.
So he concludes that most of the atom is empty space and all the atoms positive charge is found at the nucleus because from his experiment, the alpha particles returns back. And most of the mass is in the teeny central nucleus. That means the atomic mass is the proton number plus the neutron number, yes?
Yes.
Therefore, proton and neutron found in the nucleus of an atom. Based on his conclusion, most of the mass is in the teeny central nucleus. What about Bohr model of an atom?
Bohr. He said that electrons can go from energy level.
Okay, so within an atom's structure, specific energy levels exist. On that energy levels, there are electrons, and electrons move at those levels in a circular orbit around the nucleus. Therefore, the electron orbits around the nucleus. And the electron closer to the nucleus have a lower energy state than those far away. And did you remember the energy of the hydrogen atom with different principal number n?
The hydrogen?
Yeah, for hydrogen atom, the energy En is given by minus 13.6 electron volt divided by the principal number n square, yes? Did you remember from your chemistry course?
Yes, I found it on the book.
Okay, so show me that the electrons closer to the nucleus have lower energy state than those far away. For example, with principal number n equal to 1 and principal number n equal to 2, what is the energy for E1?
N2 minus N1.
So for that, minus 13.6 electron volt, yes? Divided by
Yes.
1 square is 1. And for principal number 2, for example, n equal to 2, the energy is minus 13.6 6 electron volt divided by 4, yes?
Mhm.
You will get minus 3 point something electron volt. Which one has lower energy state? E1 or E2?
E1?
E1, because it is negative number. Numbers far from the origin to the left is a smaller number. Therefore, minus 13.6 is less than minus 3 point something electron volt. Therefore, the electron closer to the nucleus have lower energy state than those far away from the nucleus. So now the electron exists between two energy states. So the energy is discrete, not continuous, because it is an integral multiples of some number. So when the electron jumps from higher energy state, E1 to lower energy state, they emit what? Radiation. That radiation is Planck's constant times frequency. Therefore, when the electron jumps from, for example, E1, he considered that E1 is higher energy level and E2 is lower energy. Then when it jumps from one energy level to another, it emits electromagnetic radiation, and that electromagnetic radiation is Planck's constant times the frequency. Is it clear?
Yes.
Good. So let's see this exercise. Two lines in the spectrum of sodium lamp have the wavelengths of 589 nanometer and 589.6 nanometer. What are the frequencies of those wavelengths? A. B. What energy changes does the transition corresponds to this energy level in electron volt? So given the speed of light is 3 times 10 to the power of, because it is electromagnetic radiation and its speed is 3 times 10 to the power of 8 meters per second square. The Planck's constant we know 6.63 times 10 to the power of minus 34 joule second, and 1 electron volt is 1.6 times 10 to the power of minus 19 joule. So what is the frequency and the change in energy? So from the equation, the speed of light is the same as the wavelength times the frequency. From that expression, for energy 1, for example, F1 is C over lambda 1, where lambda 1 is the line spectrum for sodium with wavelength is 589 nanometer. Therefore, F1 is 3 times 10 to the power of 8 meters per second divided by 589 times 10 to the power of minus 9 meter. Finally, you will get F1 is 5.093 times 10 to the power of 14 hertz. And what about frequency F2, C over lambda 2? Again, you will get the answer for this 5.088 times 10 to the power of 14 hertz. Therefore, the change in energy is E1 minus E2, which is the same as the Planck's constant times the change in the frequency. Finally, the change in energy is given by 5.58 times minus 20 joule. When we convert it to electron volt, just divide by 1 electron volt divided by 1.6 times 10 to the power of minus 19 joule. Joule by joule cancel. Finally, you will get the answer 0.35 electron volt. Is it clear?
Yes.
Good. Okay, let's see the present model of the atom. So what is the modern model of an atom?
Quantum mechanics. Quantum mechanics model.
Yeah, so first it was proposed by Heisenberg in 1900 1920, and one cannot know the precise position and velocity of a particle simultaneously. This is Heisenberg uncertainty principle, yes?
Yes.
So there are only regions around the central nucleus where there is a high probability of finding the particle, and the shape of this looks in the figure. So there is 1s orbital, 2s orbital, 2p orbital. The nucleus is in the center. So we cannot know the exact position or velocity. Velocity means, in other words, we don't know the exact position of momentum and position at the same time. So this is the current model for the atom. Is it clear?
Yes, yes.
So let's see the strong nuclear force. Do you remember from your grade 11 course, what are the four fundamental forces in physics?
Gravitational, electromagnetic, strong nuclear, and weak nuclear.
Yeah. So which one was strong force in nature?
Strong nuclear.
Strong nuclear force. And what is gravitational force?
It's the weakest.
The weakest force, and it is a force between two particles that exert each other, and gravitational force is always attractive force. And what about electrostatic force?
Electromagnetic.
Electrostatic force?
Forces between charges at rest.
Yeah. Force between charged particle is electrostatic force. So let's see the strong nuclear force in this case. It is a force that holds the nucleons together. What are nucleons?
Proton and neutron.
Yeah, proton and neutrons are nucleons. It is very short range force. Therefore, this force is has effects with order of 1 femtometer. 1 femtometer means 10 to the power of minus 15 meter, yes?
Yes.
So it is a very short ranged force, and it is the strong of the four basic forces in nature. And the electromagnetic force, the gravitational force, the weakest nuclear force, and the strong nuclear forces are the four basic forces in nature. And the strong nuclear force is created by the exchange of particles called meson. You will see this for future. There are different particles in nature, meson, neutron, positron, blah, blah. In this case, the strong nuclear force is created by the exchange of particles called mesons in the nucleus. And let's see this discussion. An approaching nucleon is captured by a nucleus only if it has a very high speed. It must have a very high temperature. Neutrons helps to reduce the repulsion among the protons in the nucleus. The strong force is the same between any two nucleons. So there in the nucleus, proton and protons are attracted by strong nuclear force, but there is also a repulsion force by electrostatic force. Yes, proton and protons are positively charged particles. They are like charges. They repel by the electrostatic force. Yes.
Yes.
That force is weak compared to the strong nuclear force, and it does not affect the attraction force between proton and proton, or neutron and neutron, or a neutron and proton. Therefore, the force between proton and proton, neutron and neutron, and proton and neutrons in the nucleus are the same. Experiment shows this. And nuclides are roughly spherical and with almost a constant density. Fermi models of nucleus give us that the radius of the nucleus is the same as 1.2 times the cube root of A, where A is a mass number, R is the radius of the nuclei, 1.2 is a constant, and the unit for this is femtometer. Did you understand this formula?
A is mass number
Yeah,
or
A is
atomic number?
mass number, proton number plus neutron number.
Okay.
And there is a mistake in this formula. It is the same as 1.2 times A the power of 1 over 3, in other words. You can check on your textbook. And the unit is femtometer. So where R is the radius of the nuclei, A is the mass number, which is proton number plus neutron number, and the femtometer is 10 to the power of minus 15 meter. And experiment suggests that the radius of nuclei from hydrogen to americium with atomic number 95, it ranges from 35 picometer for hydrogen to 175 picometer for americium. So you can calculate, for example, the radius of nuclei for hydrogen. What is the mass number for hydrogen molecule? Okay, what is the mass number for hydrogen?
1.
Mass number, proton number, and proton number plus neutron number. What is the neutron number for hydrogen?
Neutron 1.
Proton.
1.
What is the mass number A?
2.
Therefore, this number, 35 picometer, is 1.2 times square root of 2. Square root of 2 is 1.4. Let's multiply 1.2 times 1.4. Did you get this number? You can check. By the way, there is a cube root, not square root of. 1.2, the cube root of 2 is how much?
1.5.
1.5 times 1.2?
Yes, times 1.5. It's 1.5 femtometer.
1.5 femtometer.
Yes.
It is wrong. What is the cube root of 2? You can use calculator.
1.25.
1.25.
Yes.
Times 1.2?
1.5.
1.5.
1.5119.
Okay. Why 35 picometer? Here.
I don't
know. Okay, we will see an example for this, and you can check these numbers from your textbook. The mass of a nuclide is 16, therefore this is oxygen, yes? Find the radius of the nucleus. Given the mass number is 16, therefore the radius of the nucleus is 1.2 times 16 times the powers of 1 over 3. You will get 3.02 femtometer. Is this number correct? Check it.
Yes.
Okay, so in the previous slide, I think 3.5 picometer is the same as how much femtometer? Divided by 1,000, yes? 0.
3,500.
Femtometer. Okay. Okay, good. This is femtometer. Why it is larger than the radius of oxygen? The radius for the hydrogen. So check that number from your textbook, okay?
Okay.
Good. Let's see the nuclear properties. So lighter nuclei with lighter nuclei are nuclei from atomic number from 1 up to 20, where the neutron number is approximately the same as the atomic number Z. This is the same as proton number. For heavier nuclei, where the atomic number is greater than 20, for that case, the number of proton is greater than the number of atomic number. And bismuth with atomic number 83 is the heaviest stable nuclei. And nuclei from Z equal to 84, that is polonium, to Z equal to 92, that is uranium, have all radioisotopes, radioactive isotopes. What are radioactive isotopes?
They emit radiation.
Yes, those are isotopes that emit radiations. We will see in the following slides the radioactive isotopes and what they emit from their nucleus. And nucleus with Z greater than 92, greater than the uranium, all are artificial. What are artificial nuclei?
Man-made.
Yeah, they are made in the laboratory for medical purpose or extra. So let's see nuclear stability. The average number of stable isotopes per element is 3 to 1. That means per isotopes per nuclei, there will be 3 isotopes. For example, hydrogen has 3 isotopes, yes?
Yes.
What are they?
I forgot their name. Plutonium.
With the proton number, 2 is deuterium, 3 is beryllium. There is 1, that is hydrogen itself. And tin, with symbol SN, has 10 stable isotopes. This is the largest number of stable isotopes in the history of nuclei. And elements 43, 61, 84, and above have no stable isotopes at all. The stability of isotopes is affected by the ratio of the proton number and neutron number. And as Z increases, the number of stable isotopes diverges from the line Z equal to N. And the nuclear stability is also determined by the nuclear binding energy per nucleon. We will see the graph in the next slide. And as the nuclei gets heavier than helium-2, their net binding energy per nucleon grows until it reaches that of the iron with mass number 56. Then the increase in the disruptive energy of the electrostatic force becomes greater than the increase in the net binding energy. So to reduce this disruptive energy, the weak interaction allows more neutrons to be added. At some stage, the only way for the nucleus to reach a lower energy state becomes to emit particles. This is called radioactivity. Radioactivity is the spontaneous emission of particles or radiations from the nucleus. And this graph shows the number of neutron versus atomic number. The x-axis is atomic number and the y-axis is the neutron number. And in the y-axis to the right, when we go up, how many times takes to be the atom to be stable? For example, for lower neutron number or atomic number to be stable, they will take around this is 10 100 or picosecond, then it increase 1 second is around this area, and it takes, for example, for this case 10 to the power of 14 years to be stable for that nuclei when the number of nuclei increases. So this figure is the nuclear stability, neutron number versus atomic number. You can see the detail of this graph on your textbook. And the average net binding energy per nucleon is given in this graph. Butene, this is the maximum net binding energy. The maximum net binding energy is for iron with mass number 56. It increases with number of nucleons, and it gets maximum for the iron, then it declines for the uranium with different isotopes here. Is it clear, the previous slide?
Yes.
Good. Let's see radioactivity. What is radioactivity?
Emission of particle or radiation.
Yeah, radioactivity is a process that enables a nucleus to become stable by emitting particles or radiation. So when a nucleus splits up into two almost equal parts, it is called nuclear fission. For example, the daughter nuclide is uranium with mass number 235 plus neutron number. When we add neutron to the uranium, we will get cesium with atomic number 55 plus rhabdium with atomic number 37 plus the neutron. The daughter nuclides are cesium and rhabdium. It is impossible to predict when a given atoms will decay, and it occurs randomly over space, but the average decay rate can be predicted when a large number of similar atoms are there. The decay of the nucleus is independent of the external effects, and it is governed only by the energy state of the nucleus. And two small nuclides can be fused to form a bigger nuclide. We call this nuclear fusion. For example, hydrogen plus hydrogen gives helium. This reaction takes place in the sun, for example. When hydrogen is combined together, they will produce helium. This process requires high temperature and pressure. And let's see the types of nuclear radiation. How many types of nuclear radiations are there?
3.
What are they?
Alpha, beta, gamma.
Alpha and beta are particles, and gamma is radiation, yes?
Yes.
Alpha is the same as the helium atom, and it is removed or radiates from the nucleus of an atom. Again, beta can be electron or positron. When with -1 charge, it is electron, and when it is with E plus, we call it positron. And this is different from atomic electron. What is atomic electron?
Atomic electron. What?
I mean, we have, for example, we have sodium with atomic number 11. Write the electron configuration for the sodium.
281.
281. So what is the valence electron for sodium?
1.
1. That is the atomic electron that revolves around the nucleus, yes? We call that atomic electron, and this beta is different from that electron because this electron is from the nucleus of an atom. Is it clear?
How?
This beta electron is from the nucleus. There is no electron in the nucleus, yes? So particles will emit beta particle, sometimes called electrons, to be stable, and this electron is different from the atomic electron. And the energy for this beta particle is continuous, and the energy for that electron is discrete. You will see the detail when you go to higher education. Did you understand the difference?
How it is discrete and continuous?
I mean, for hydrogen, for example, we have seen in the Bohr model, the energy is discrete and given by minus 13.6 over n square. For this one, for beta particle, you will see the detail for the future. The energy is not like that one. The energy is continuous for this one, and it is different from atomic electron.
Okay.
Because this electron is from the nucleus.
It's produced from the nucleus?
Yes, when in the nucleus, for example, when the neutron decays to proton, what happens? Write the equation for the decay of neutron to proton.
Equation what?
The decay of neutron into proton in the nucleus.
How we write the equation?
Okay, neutron gives proton. Okay, it is not balanced because for neutron there is no charge, yes?
Yes.
But for the proton there is plus one electron, yes?
Yes.
To be conserved, you have to add E minus from left.
Yes.
Or neutron gives proton plus electron. Now the charge is balanced, yes?
Yes.
That electron, we call it beta particle.
Okay.
So this neutron, this beta particle or electron is from the nucleus. It is different from the electron that you now, from your knowledge, the electron that orbits around the nucleus. So let's see let's compare the ionization ability for alpha particle, beta particle, and gamma particle. The ionization is strongest for alpha particle, weak for the beta particle, and weakest for gamma particle. What does ionization means? Hello? Hello?
Hello?
ይሰማል?
ይሰማል።
ionization ማለት ምን ማለት ነው?
When proton goes out?
Yeah, for example, when alpha particle is positively charged particle with helium 2 plus, yes?
Yes.
When it comes to a certain surface, maybe human body, it ionizes the body, yes?
Yes, it takes
So
the proton.
that ionization is strongest for alpha particle, and beta particle also ionize, but the strength compared to alpha particle is weak. And gamma particle is neutral, yes? It doesn't ionize any particle. Maybe it passes through the body, but the ionization is weakest compared to the beta and alpha particle. Good, and each has ionization ability. Alpha particle have the strongest ionization ability. They enter only a few centimeters into any body, completely absorbed by paper or skin, loses kinetic energy very quickly. And the beta particle, the beta particle is emitted when a neutron decays into proton, that I have told you in the previous slide. Beta particles are emitted when the neutrons decay into proton, weaker ionizer, therefore they enter a body better than alpha particle, absorbed by the thin sheet of aluminum. Gamma rays are high energy electromagnetic radiation, poorest ionizers, never completely absorbed, but significantly reduced by several centimeters of lead. So for shielding for beta particle is most probably lead, and dangerous to human, they affect the cell. They may cause cancers for human beings, yes. And cancer is treated by this electromagnetic radiation, and they are the cause for cancer. Is it clear?
Yes.
Good. Let's see gigamolar tube. What is gigamolar tube? It is a device that detects all types of radiations. It detects alpha, it detects beta, and it detects gamma radiation. There are various forms of detectors, sodium iodide, HPG, blah, blah. You will see this when you go to higher education. And let's see mass and energy relationship. The energy and the mass are related by the Albert Einstein equation. The energy is given by the mass times the speed of light, c square, where this is the speed of light. And as I have told you last time, the sum of mass of the nucleus minus mass of the nucleus gives the mass defect delta M, where mass defect means that mass of the whole is less than mass of the parts. Because how this is, okay, good question. Okay, so do you know the chemical reaction? For example, carbon plus oxygen gives carbon dioxide.
Yes.
There is also the nuclear reaction. The nucleus of carbon plus the nucleus of oxygen gives the nucleus of carbon dioxide. For that reaction, what is the energy required for the nuclear reaction? Binding energy is the energy required to form that reaction, and that binding energy is the same as the defect mass minus the mass of the nucleus times the speed of light c square gives the binding energy. So mass of the part ስንመጣ ለምሳሌ carbon plus carbon, for example, the mass of the nucleus for proton, neutron of carbon 1 plus the mass of the neutron and proton for carbon 2 is greater than the mass of the nucleus, that means the carbon molecule. There is carbon molecule? No, yes? You can take an example for nitrogen. Nitrogen plus nitrogen gives nitrogen molecule. And the mass of the part is greater than mass of the whole. We will see this by an example. That energy, that defect mass goes for the binding energy, yes?
Yes.
The energy to combine to nucleus or required to combine to nucleus, or the energy to separate to nucleus is a binding energy. Thus mass defect goes for the binding energy. And the mass of the nucleus is the mass of the atom minus mass of the electron, because the electrons revolve around the nucleus, yes?
Yes.
So, for example, for carbon-12 nucleus, calculate the mass defect, calculate the net binding energy in electron volt. What is a mass defect? The mass defect is given by the mass of the sum of the mass of each nucleus minus the mass of the nucleus. This is a sum of mass of each nucleon, that means proton, neutron, of carbon, and this is the mass of the nucleus for carbon. Therefore, in the carbon atom, by the way, we have seen this last time, the mass of neutron in atomic mass unit is 1.008665, and the mass of proton is 1.007276 atomic mass unit. So for the carbon, there are 6 proton and 6 neutron, yes?
Yes.
So these 6 times 1.008665 plus 1.00726 is the mass of the nucleus, mass of the proton in the proton, minus the mass of the nucleus. The mass of the nucleus, the mass of carbon-12 is 12 atomic mass unit, yes?
Yes.
So we have to subtract the mass of the electron. There are 6 electrons in carbon, yes? 6 times 0.000549. Finally, you will get the difference is not 0. So the mass of the part is greater than the mass of the whole. And this is a defect mass, which is 0.09894 atomic mass unit. And we have seen from the previous slide in the last week, 1 atomic mass unit is the same as 1.660540 times 10 to the power of minus 27 kilogram. You can change this into kilogram by multiplying by this number. Finally, the defect mass is 1.642938 times 10 to the power of minus 28 kilogram. Have you seen this mass defect? This mass defect contributes for the binding energy, and this mass times the speed of light gives the net binding energy. So the net binding energy is the same as the defect mass times the speed of light. C square, therefore 1.642938 times 10 to the power of minus 28 kilogram times 3 times 10 to the power of 8 meters per second, Joule square. Therefore, the net binding energy in Joule is 1.478644 times 10 to the power of minus 11 Joule. And you can change this into electron volt, 1 electron volt. How many joules are there for 1 electron volt? Multiply 1 electron volt divided by 1.6 times 10 to the power of minus 19 Joule. Joule by Joule cancel. Finally, the binding energy in electron volt is given by 9.24 times 10 to the power of 7 electron volt. Change into mega electron volt. Mega means 10 to the power of 6. Therefore, it gives 92.4 mega electron volt. Is it clear?
Yes.
This is the energy required to combine the required to disassemble or to combine two nucleuses together. So let's see the reaction, nuclear reactions. Nuclear reaction balance whereby the total charge must be conserved because charge is always conserved. Total nucleon number is conserved. The total number of nucleon for the reactant and for the product must be the same. And radiations are emitted to conserve the energy. The energy should be conserved. For that case, the radiation will be emitted. Just like the chemical reaction, you can balance chemical reaction by LCM method or by assumption, yes. Just like that, for nuclear reaction, charge must be conserved, total number of nucleon must be conserved, and radiations are emitted to conserve energy. For example, for this nuclear reaction, uranium-235 plus neutron give us X for mass number here times the rhabdium plus 139 cesium plus twice of the neutron plus the energy. So what is X in this reaction? Huh?
235 minus 1.1.
In the reactant part, neutron has mass number 1, yes?
Yes.
So 235 plus 1 in the reactant. In the product, for the rhabdium, X plus 139 plus twice of neutron means 2 times 1
Yes.
mass of the neutron. So you can rearrange this equation and you can calculate for X. Therefore, X is the same as 236 for this one minus 141. At the end of the day, you will get 95. This is the value of X to conserve the nucleon number. Yes? Let's see exercise 10. Determine the mass defect and the energy released in the following fusion reaction. Uranium plus neutron gives us barium plus krypton, Kr times 3 neutron plus energy. What is the mass defect and the energy released? Given the mass of uranium in terms of atomic mass unit, 235.0349, mass of the barium 140.9144 atomic mass unit, mass of Kr is 91.9262 atomic mass unit. This is a given information to calculate the defect energy and the energy released. Yeah. So the mass defect delta M is given by the mass of uranium in terms of atomic nuclei from the previous slide, 235.0439, plus the mass of the neutron is 1.0086 minus mass of the part, and the product gave us mass of barium in terms of atomic mass unit 140.9144 plus for Kr 91.9262 plus we have 3 neutron here, 3 times the mass of the neutron. And finally, you will get the defect mass is 0.184 atomic mass unit. You can change into kilogram. 1 atomic mass unit is the same as 1.6605 times 10 to the power of minus 27 kilogram per atomic mass unit. Atomic mass unit cancel, you will get the defect mass in kilogram 3.0553 times 10 to the power of minus 28 kilogram. And B, what is the energy released? The energy released is the same as the net binding energy, which is the mass defect times the speed of light. And you can convert one atom from the last week slide. 1 atomic mass unit is the same as 931.5 mega electron volt. To change this into energy, just multiply 931.5 mega electron volt per atomic mass unit. And finally, the energy released is 171.4 mega electron volt. Is it clear?
You converted the speed of light?
Yeah. In energy, let's go back to the last week's slide. De Broglie. Okay. I think here it is. 1 atomic mass unit is 1.660540, and there is a number back of this slide. You can check from your textbook. 1 atomic mass unit in terms of energy is 931.5 mega electron volt. Do you have a textbook with you?
Yeah.
Check it on the last page or in the summary part. You can check it, or in the radioactivity part.
Yes, I got it.
You got it. So 1 atomic mass unit is the same as 931.5 mega electron volt. So this is the energy released in mega electron volt. So what time is it now? Okay. We have studied almost 1 hour. So, okay, let's, if it is, do you have any question up to this?
No,
No. So the next part is, I think, the half-life. It will take up 30 minutes or more than that. So let's see this next week. Or not Saturday, not next week. Yes?
Okay.
Yeah, the half-life part. Try to study those parts, and I'll give you an exercise or a quiz for this part.
Half-life is easy. We studied it on chemistry.
Okay, we can see it now for 5 or 10 minutes. Yes, it is easy.
Okay.
Okay. So what is half-life?
The period in which the atom, the half of the atom decays after the nucleus.
Okay. You have to stop here. Why it slides? Yeah. Okay. Come on, guys. Okay. Slide unten below, you know. Stop alarag below, you know. Slide yaraga. Okay. So half-life. Half-life is the time taken for radionuclides to decrease by 1/2. Yes. So before
Yes.
that, what is activity?
Activity?
Mm-hmm.
What activity?
What activity? Radionuclide activity.
Mm,
Yeah, now it's fine.
yes.
Good. So, at time t-half, the number of nuclide is n0/2, yes?
Yes.
So let's substitute in the original equation. At time t-half, when we substitute the time is t1/2, the number of nuclide left is n0/2. We can cancel n0 both sides, yes? So 1/2
Yes.
is the same as is the power of minus lambda t-half. 1/2 means to the power of -1, yes?
Mhm.
Times is the power
Yes.
of minus lambda t-half. Take both sides the natural logarithm ln. Ln to the power of -1 is the same as ln is the power of minus lambda t-half. Ln E is 1, yes?
Yes.
So the second term is minus lambda times t-half. The first term is to the power of -1. Using the law of exponential logarithmic function, we can take -1 to the left. Minus ln 2 is the same as minus ln minus lambda times t-half. We can cancel both sides the negative sign. Therefore, ln 2 is the same as minus lambda, lambda times t-half. Both sides, divide both sides by the decay constant lambda. Therefore, the half-life is given by ln 2 divided by the decay constant lambda. Is it clear?
Yes. Yes.
Where ln 2 is 0.693 divided by lambda is the half-life. And as an exercise, what is the half-life of carbon-14, where the decay constant is 3.84 times 10 to the power of -12 second?
0.693 over lambda.
Yes. Therefore, it gives 5,724 years, the half-life for carbon-40. Okay, the half-life is clear. I will give you a quiz for that part. And let's see use of radioactive isotopes. What are the use of radioactive isotopes? So it uses to treat cancer. Example is iodine 131 in the form of iodide chloride for thyroid cancer, and the tectanium TC99 is used for gamma ray scanning and checking the functions of different organs inside our body because of its low energy. And this is polonium commonly used for atomic power supply in space shape, and to generate electricity in nuclear power station. Are there nuclear facilities in Africa? How are radioactive isotopes used in dating objects? So archaeologists used the half-life to determine the years of the fossil, yes?
Yes.
So I think this is the last slide. And the problems posed by the nuclear waste. So isotopes used in the nuclear power stations have long half-lives, and they emit dangerous radiation all the time because they emit alpha, beta that causes cancer. So too much spent nuclear fuel posing dangers as short-term radioactive material, contaminating underground water where nuclear waste is stored in the underground steel and concrete containers. So the radioactive causes for cancer even, and the cancer is treated by radioactive material, yes?
Well,
For example, there is here in Addis radiotherapy center in Black Lion Hospital. There is cobalt-60 there for cancer treatment. If we lost it somewhere where most of the population is work there or blah blah, if the people are exposed to that radiation, again they will cause for cancer, yes?
yes.
So you can read the detail for the problem by the radioactive isotopes and the uses. I think this is the last slide for chapter 8. Do you have any question up to this?
No, thank you.
Okay, good. So